First of all, I would like to thank you organizers for invitation and giving me a possibility to talk during such nice and interesting meeting. The main aim of my talk is to present solutions of the Yang-Baxter equation with universal algebra point of view and show some advantages of such approach. This lecture is the result of joint work with Przemysl Jedliczka and Anna Zamojska-Dzienio. As it was been already shown by previous speakers, there are different algebraic structures closely related to different kinds of solutions. In particular, yesterday, Charlotte and Hilaria talked about associative structures called semitrusses related to one-sided non-degenerate solutions. Now, I plan to talk about non-associative structures, which are in one-to-one correspondence with both-sided non-degenerate set-theoretical solutions. To establish notation, I will focus on set-theoretical solutions presented by Drinfeld, and I will understand a solution as a set with a mapping R, which is determined by two components, sigma and tau, and this mapping R is defined by related braid relation. Taking into account different additional properties of this mapping R, we can consider different kinds of solutions. Let us recall some of them. So in particular, we say that a solution is non-degenerate if all sigma x and tau y are bijections, is involutive if mapping R square is identity. It is called invertible of bijective if this mapping R is a bijection, and is called derived if all sigma mappings are equal to identity mapping, or all tau mappings are identities. Algebraic structures which are closely related to non-degenerate set-theoretical solution are called Biracks. Biracks are algebras that appear in low-dimensional topology. About 2 years ago, Kaufman introduced the virtual knot theory, in which Biracks play a similar role as racks in classical knot theory. At first, I present the definition, equational characterization of Biracks, and this following equational definition of Birack was given first by David Stanowski. By Birack, we will understand an algebraic structure with 4 binary operations: left multiplication, left division, right multiplication, and right division. And this structure satisfies these following 5 identities, 5 conditions. The first one means that our structure with first 2 binary operations is a left quasi-group. This means that each equation of the form x multiplied by u equal to y has a unique solution, which is expressed by the left division. And the second condition means that this set with remaining binary operations of right multiplication and right division is a right quasi-group, which means that the equation u multiplied by x equal to y has a unique solution expressed by the right division. If our Birack satisfies some additional identities, for example, if these 2, 1 are satisfied, we call such Birack an involutive. In this case, we can note that the second multiplications are uniquely determined by the first one and divisions. For example, the right multiplication is uniquely defined for involutive Biracks by left multiplication and left division. And we call a Birack idempotent if the result of both multiplications, left and right, x by x is equal to x. It immediately forces that the same condition is also true for left divisions. It is easy to notice that for both one-sided quasi-groups, the mappings of left and right translations are by some particular element x are defined in a very natural way. And because we have 2 one-sided quasi-groups, so all these translations are bijections, and they are generate 3 types of groups related to a Birack. Left multiplication group generated by left translations, right multiplication group generated by right translations, and the general multiplication group which is generated by left and right translations. How to connect a Birack with solution? Having a solution, we have a mapping R defined on some set X, and for sake of simplicity, let's change the denotation. Let us denote the mapping sigma by circle operation and the mapping tau by bullet operation. Because for case of non-degenerate solution, our sigma x and tau y mappings are bijections, so our left and right translations with respect to circle and bullet operations are invertible. So of course, we have inverses of them. And when we define by division of with respect to the left operation, the inverse of the left translation, and by the by the right division, the inverse of the right translation. So instead of classical presentation of the solution, we can present it in the equivalent form, and at the same time we obtain a new algebraic structure with 4 binary operations, and by properties of the braid relation, they satisfied all axioms of a Birack. Because they are bijections, we have 2 one-sided quasi-groups, and by the properties of braid relation, we have remaining 3 rest axioms. So, summarizing, each non-degenerate solution of Yang-Baxter equation yields some corresponding Birack. The converse is also true, because if we start with a Birack, then we can, in very natural way, define a mapping R. When we take as an operation sigma the result of left multiplication x by y as a first coordinate of this mapping, and the result of right multiplication as a second coordinate, we obtain a non-degenerate solution of the Yang-Baxter equation. So we have the result formulated by Fan that there is a one-to-one correspondence between non-degenerate solutions of the Yang-Baxter equation and Biracks. Additionally, if a solution is involutive, so the correspondence Birack is of course involutive, and vice versa. This theorem of Fan gives us a very useful correspondence, which is crucial for my next considerations, because thanks to this result, thinking about solutions, I can always refer to corresponding associated with this solution Birack. Okay, let us see for some very simple examples. Everybody knows Lubashenko solution, which is defined on some non-empty set by 2 commutative bijections, and using left multiplication as a first mapping F, and right multiplication defined by the second bijection G, we immediately obtain a Birack, which is called a permutational Birack. In the case if all bijections F and G are equal to the identity mapping, this Birack is called projection. The second example is given by Vada solution, which is built on any group, and when we take as a left multiplication the result of the first component of the operation R, and as a right multiplication as a second component of the mapping R, we obtain a Birack, which is involutive if and only if the elementary, group G is an elementary abelian 2 group. So to Vada solution, the corresponding Birack is a Vada switch, or Vada biquandel, as it was called by Fan. As everybody well know, Ettinghoff, Shedler, and Soloviev introduced for a non-degenerate involutive solution the equivalence relation of retraction relation, and using properties of the structure group, they showed that the quotient set by this relation can be endowed with a structure of a solution. This new solution they called retraction of the solution. They also showed that equivalently, this relation can be defined not by tau translations, also by sigma translations. In the language of corresponding to this solution Birack, this simply means that such relation defined by left translations corresponding to the left quasi-group is a congruence of this structure, this algebraic structure. Let us recall that by congruence, we understand an equivalence relation defined on a set X, and we say that this congruence, this relation is in this particular case is a congruence on a Birack if this relation is compatible with all four operations of the Birack, which is mean that, for example, if X is in relation with Y and Z is in the relation with T, it means that the result of left multiplication of X and Z must be in relation with the result of this multiplication Y by T. And it is for all operations of Birack. And by general results from the theory in universal algebra, if a relation is a congruence of a Birack, then the quotient set is the equivalent, is again a Birack built on the equivalence classes of this relation, and such Birack is called the quotient Birack. So taking an involutive solution, we construct corresponding Birack, and this retract relation defined by Ettinghoff is a congruence relation of such Birack. But in general, for non-involutive Birack, it is not true. Let us consider the following example built on a 5-element set with left and right multiplications defined in the following way. It is easy to check that, in fact, that this Birack is non-involutive. So the corresponding solution is also non-involutive. And this left retraction relation, in this case, is not a congruence of this particular Birack, because we can see that left translation by 0 and by 1 are equal. So 0 and 1 are in relation, and 2 and 3, the translations by 2 and 3 are also equal. So 2 and 3 are in relation, but the result of multiplication 0 by 2 is equal 1. 0 by 2 is equal to 1, and when we multiply 1 by 3, we obtain 4. But the translation by 1 is not equal to translation by 4. So 1 is not in congruence with 4. So it proves that this relation is not a congruence of this non-involutive Birack. But of course, for an arbitrary Birack, we can define dual version of the left retraction, which was defined by left translation, and we can define the right retraction relation defined by right translations. And we can also define the third relation, which is the intersection of the left and right version. So this relation is defined by equal, the two elements are in the relation if and only if the right and left translations by these elements are equal. Clearly, if a Birack is involutive, these relations are, of course, all equal and all are congruences of corresponding Birack. For arbitrary Birack, this new equivalence relation we will call a generalized retraction. Victoria Lebet and Landro Bendramin considered a finite non-degenerate invertible solution. Solution in the mapping R is a bijection. And they showed then that in this particular case, this mapping R induces a solution on the quotient set by this generalized retraction. So in fact, they showed that for a finite non-degenerate invertible solution, the corresponding the relation of the generalized retraction is a congruence of the corresponding Birack. Nevertheless, the generalized retraction is a congruence even in the more general case, but it is true that the generalized retraction is a congruence of an arbitrary Birack. The proof of this theorem is very technical and rather complicated, but this theorem directly shows that the retraction of any solution, non-degenerate solution, not especially involutive or invertible, is well defined, and for any solution we can define its retraction, which is of course a solution defined on the quotient set by this generalized retraction. Moreover, the Birack corresponding to this retraction is the retract of the quotient Birack defined on the equivalence classes of the generalized relation. Similarly, as for classical case of involutive relations, involutive solutions, we can define iterated retraction in the natural way. Okay. Among all possible non-degenerate solutions, two types of them are particularly well studied. Involutive ones, which I mentioned before, and derived solutions. If we take, for example, a derived solution with all sigma mappings being identity mapping, We can note that there is some special correspondence between tau mappings. There is some kind of commutativity, some kind. But it is also true, this correspondence holds not only for tau operations, but also for any bijection from the multiplication group of a derived solution. This is also true for any element from this group. When we take a second version of a derived solution, so take in which all tau operations, tau mappings are the identity mapping. So we obtain the dual version of this correspondence for any bijection from the multiplication group of the solution. Distributive solutions are not derived, but they are some generalization of the idea of a derived solution. A solution, we will say that a solution is distributive if both these conditions are satisfied for any element from the multiplication group. It means that each bijection from multiplication group of the solution is in fact an automorphism of the solution. What we can say about the Birack, which corresponds to the distributive solutions. Of course, such structure must inherit some all properties of distributive solution, and we will call a Birack a left distributive if its left quasi-group is in fact a left rack. So if the following left distributivity is true in this structure, and dually it is right distributive if right one-sided quasi-group is right rack, which means that such identity is true in this structure. And we say that a Birack is distributive if it is left and right distributive. It is easy to notice that each permutational Birack is distributive. And in the case of Wada switch, such Birack is left distributive if and only if for each element its square belongs to the center of the group, and it is right distributive if and only if additionally each element has has order equal to 4. So immediately we can see that each right distributive Wada switch is of course left distributive. Another example, quite important for distributive theory, distributive Biracks, is constructed using two racks, left and right ones. If we take a left rack and we define two additional operations of which we can define them by right translations, and when we take right translations equal to the identity mapping, we obtain with these 4 operations a left derived Birack. Dually, if we start from some right rack, we can define left translations as identity mappings, and in this way we obtained a right derived Birack. Their product is a distributive Birack with fine property, additional property. The multiplication group of this particular distributive Birack, built on the product of the left and right derived Biracks, is isomorphic to the product of left multiplication group of this Birack and the right multiplication group. Okay, if we take a Birack, so left distributivity for this structure means that all left translations are automorphisms of the left rack. And dually, because all are symmetrical, right distributivity means that all right translations are automorphisms of right, corresponding right rack. But we have even more. If we start from a distributive Birack, for each bijections of left and right, each bijections which are left and right translations by any elements of set X are automorphism of the whole Birack, not only of particular one-sided quasi-group, but of the whole Birack. Additionally, by this first result, we obtain that all three groups of left multiplication, right multiplication, and the general multiplication group of the Birack are normal subgroups of the automorphism group of the whole Birack. In particular, the commutator group of left and right multiplication groups is trivial. Okay, let us back to the retraction relation. As I some minutes ago showed that for general case, these three relations need to be congruences of the Birack. They are in the involutive case. But in the case of one-sided distributive Biracks, the situation is a little different. And the first relation, the left retraction relation, is a congruence of a left distributive Birack. And additionally, this quotient Birack, but this left retraction relation is equal to the left derived Birack of the quotient Birack by this particular relation. Of course, we have the dual symmetric version for the right distributive Birack, and in this case, because it is a congruence of the right distributive Birack, the quotient Birack is the right derived Birack of the quotient Birack. And for a distributive Birack, when in this case, our algebra is simultaneously left and right distributive, of course, we know by general result that this relation in this case is a congruence, but the quotient, the retract, the quotient Birack is in this case idempotent. Okay. Additionally, I said that in general case, the proof that this generalized retraction is in fact a congruence of a Birack is rather complicated. But in the case of distributive Biracks, which also are in general is not, they are need to be involutive, is, I can say, almost straightforward. Okay. Similarly as for classical relation of retraction, we can also define a multi-permutation. We can also say about multi-permutational level of a Birack, and we say that a Birack is of multi-permutational level k for some natural number k, if k is the smallest integer, such that kth retract with respect to this generalized retraction relation is one element. As probably most of you very well know, that Tatiana Gateva gave a characterization of involutive solutions, which are of multi-permutational level k. When we translate her result, formulating for solutions for corresponding Biracks, it is true that for an involutive Birack, such Birack is of multi-permutational level k if and only if it is so-called left k permutational. This means that such Birack satisfies some new equation. If you look for the both sides of this formula, you can see that the difference between left and right side is only in the most middle variables. And this means that we can take in this place arbitrary elements. It is worth to notice that in the case of idempotent involutive Birack, this identity is equivalent to the left k reductive one, because if we put instead of x, xy, so because this Birack is idempotent, we obtain that the result of multiplication is equal to the this variable. So our first equation reduced to the simpler form. We were able to formulate this theorem in the case of distributive solutions. So we formulated this result not only for involutive case, but also for distributive. And we obtained even a little more. But first of all, because in this case, left and right distributivity in general case are not equivalent, we need symmetrical definition of right k permutational and right k reductive. In the case of arbitrary Birack, the difference is only for different operations of multiplication. We take right version of these equations. And we will say that a Birack is k permutational or k reductive if it is left and right k permutational and or k reductive respectively. So if it satisfied these presented identities. And using the similar ideas, Tatiana, we proved that for a distributive Birack, and k which is greater than 2 or equal to 2, a Birack is a distributive Birack is k permutational if and only if it is k reductive, or if and only if it is k if it is of multi-permutational level k, or if and only if, this is the new result, the multi-permutation, multiplication, the general multiplication group of this distributive Birack is nilpotent of class at most k minus 1. Let us note that this theorem is not true for the case of k equal to 1, because for the permutational Birack with mappings f or g not equal to the identity mapping, the retract of this Birack is of course one element, but the multiplication group is of course non-trivial. Moreover, our theorem cannot be generalized for non-distributive Biracks. By results of Agata Smoktunovich, there exist involutive solutions which are multi-permutation, but their multiplication groups are not nilpotent. And on the other hand, there are not permutation solutions, involutive solutions, with their multiplication groups nilpotent. At the end, I would like to say a few words about distributive solution or equivalently distributive Biracks, which are simultaneously involutive. In this case, Biracks and equivalently solutions are quite simple for they have quite simple form. At first, let us note that each involutive Birack is left distributive if and only if it is right distributive. Such involutive Birack, the distributive involutive Birack, can be equivalently defined as a left two reductive one. So such in which the following identity is true when we multiply x by y and by z, it is equal to y multiplied by z, or equivalently by the left translation by the element L x of y is equal to the translation by y. And the quotient of the distributive involutive Birack is a projection Birack. Gateva-Ivanova showed that each non-degenerate distributive involutive solution is always a multi-permutation solution of level 2. Collecting all these results together and translate into the language of solutions, we can say that in the case of non-degenerate involutive solution, the following conditions are equivalent. The solution is distributive if and only if it is two reductive in this sense, and the retraction solution is the trivial solution. In the case of distributive involutive Biracks, we can also present very simple construction of such Biracks and in consequence such solutions. It is true that each involutive distributive Birack can be constructed as a disjoint union of a family of abelian groups, and we can present an explicit form of left and right operations of this Birack. If we translate the result into the language of solutions, so we can obtain that each non-degenerate involutive distributive solution can be constructed on the disjoint union of abelian groups, and mappings sigma and tau are defined in the following way. This means that if we have this disjoint union of arbitrary number of groups, this is true also for non-finite solutions, and we take I and j component, and when we take element x from the component I and the element y from component j, so to each pair of numbers n and I, we have generators of these abelian groups, and these operations of sigma and tau are defined by these generators. If x is from component I and y is from component j, so we add to the image of the sigma x of y is the sum of this element y plus to appropriate generator of one of these abelian group. In this case, from the abelian group with subscribe j. In this way, we using this result, we can construct for any finite non-degenerate involutive distributive solution for arbitrary cardinality n. We have to find all partition of this number n, define all abelian groups or appropriate cardinality, take their generators, and we can construct such solutions. We also can formulate the isomorphic theorem in this case, so we are able to recognize which of such solutions are isomorphic or not. Finally, you can compare the number of involutive non-generated solution with respect to the such which are multi-permutational of level 2 and which are how many of them are two-reductive or equivalently distributive. So we can see that for solutions of small size, almost all multi-permutational solution of level 2 are distributive. Here is the list of references which are used preparing this presentation, and this is all, and thank you very much for your attention.